Hello everyone, today I will present to you about our product, which is Remote Energy Monitoring and Switch. We are from Team Energy Saver. Alright, so let's start the presentation with what is our product. So our product aims to monitor the energy you use in your house. Depends on which device you install it. It can monitor the energy, power, everything that consumed by that appliance. So we show the energy use to the user through the form of costing instead of energy. Because you tell them you spend 20 ringgit for this device for 1 hour instead of you spend 20 kilowatt hour for this hour. Cost is more convincing than the kilowatt hour. The next one is we want to let the user to be able to remote monitor and control their house appliance when they are away from home. So it is possible that someone forgot to switch off their appliance, or they don't know if they already switch off their appliance when they are away from home. So with the app, as you can see from the right side, you can actually see the current state of the appliance. So next one, we also want to alert the user for excessive use of energy. Our product want to show the user the trend of the energy they're using. By using it, they can actually know are they spending too much or too less by looking at the trend. Next one, we also want to let the user to have the easy access to the power switches. For example, I'm laying on my sofa and I want to turn on my ceiling fan, but I'm so lazy to go to the switch. So instead, I can actually use our product to turn on the ceiling fan. The last one is, it's also possible for our product to locate the ignition source in case of fire. So for example, there's a fire and you don't know which place started the fire. So you can actually track back by looking at the trend. For example, my fridge suddenly have a huge spike in fire. Huge spike in current. So I can know that this fridge is actually causes the fire due to short circuit. As you can see from the right side, the app for the motor pump, our app will show them how much power is currently consuming, and then how much cost this device already costing since they are started. And then in the middle, there is a button which you can actually on off the appliance remotely. And lastly, at the bottom, there is a graph which will show the user the trend of energy they use. Alright, so let's go to our problem statement. So first one, we aim for the people that are having a high electricity bill and they want to track which device causes them to pay such a high electric bill. And the next one is we want to prevent the wastage of energy. For example, people who tend to forget to switch off their appliance when they are not at home, as shown in the third point. And then for the last one, we also aim for the people who are lazy and then they wish to control the whole house with only their phone. It is possible with our product. Alright, so let's look at our bill of materials. So we can see that the total cost for one set of our product is around 50 ringgit. And for the non-MCU, although it's 20 ringgit, but it is actually possible to let us add on more relay. For example, if we have multiple devices near each other and we want to add more relay, we can only pay for few relay and we can use it for more devices. For AC current sensor, it's actually rated for 100 ampere, which means if we use it at a low power place, we can actually buy a lower rating one. In the end, this means the bill of our project is actually very flexible. Lower power means lower cost. Alright, so let's go to the methodology. How are we going to achieve this outcome? For the first one, we have our, as you can see from the right side of the circuit, we have the voltage sensor, current sensor, and relay. So first one, we will use the oscilloscope to measure the voltage and current that is consumed by the load. From there, we can also find the phase shift. And then we have, after we have the parameter, we can actually insert them to the coding for the NOT MCU. And then from the NOT MCU, by looking at the output, we can calibrate the output based on the data in the oscilloscope. So we will have an accurate reading of our product. And then if we have voltage, current, phase shift, it is possible for us to find the power, energy, and also costing for this appliance that we are installing. Alright, so let's go to the circuit. You can see that since there are voltage sensor and current sensor, there are two analog sensors. So this NOT MCU cannot support it because we only have one analog pin. So we use an analog extender to give it more analog pin. And then we use the relay, a digital pin, to switch on and off the AC load, which in this case is a fan. And then from at the right side here, you can see that some capacitor and resistor. This is because the current sensor output is AC, and we don't want to let the AC to enter the NOT MCU because that will fry the board, burn the board. So instead, we use the voltage divider rule with a capacitor to make it into a DC value. So the current sensor output will change into a voltage form, and then the voltage value will be read by the NOT MCU. And in the end, we can extract the voltage value into the current value. Here is the more detailed version of the current sensor output. Since the current sensor output is only current, and if we use them without a burden resistor, it will cause a large voltage to go into the Arduino due to the infinite resistance. Thus, we need a burden resistor, which in the case, I use a 20 ohm resistor because the NOT MCU voltage is 3.3 volt. So you can see that I also use a voltage divider rule here. So the voltage reference for my burden resistor will only be 1.65 volt instead of 0 volt. So this can make sure that the negative cycle of the CT, the current transformer output, won't go inside the Arduino, but instead they will go to the path I provided, which is the capacitor here. So let's see at the bottom here. So we can see that if we use a 20 ohm burden resistor, the peak-to-peak voltage to Arduino is only 2.828 volt, which is lesser than the 3.3 volt, which means this voltage won't burn our board. Alright, so now I will show you the app we do. So the app we are using is Blynk app. So first of all, let me show you that. Now I'm connected to my house Wi-Fi, so I'm going to change it to my mobile data. And to show you, I didn't open my hotspot, which means the project is not in the same network with my app, which means we can actually remotely control the project while we are outside, as long as we have the internet connection. So let's see at our app. Okay, so you can see that we have some device here. This one can be add more. So now we have motor pump, kitchen light, or bedroom aircon. It's up to you where you want to install the product. So for example, now my load is a 8-watt motor pump, because this is just for an example, because I have this only on my hand, so I'm using it as my load. And here in my app, you can see the power that will consume by this load. Currently it's in offset, and you can see the power drawn is only like 0.02 watt. And then next one is the cost. So our project can record the cost that is consumed by this slot if you install it at the switch of this slot. This one is the power switch. When you turn it on, this slot will turn on. Lastly, we have the graph. So this graph can actually help you track the activity of the lot using and how frequent you use the lot. So in case you want to track back how is the lot performed in past few weeks, you can actually go to 1 week and see the condition of it. Now let's go to the hardware. Here I have the Node MCU. This is the component that connect my project to the internet. And next I have a relay. This relay can act as a switch that is controlled by acts as a switch for this lot. Here I have a current transformer. This transformer can use to monitor how much current is going into the lot, and then the output of this current transformer will go to this burden resistor and then change it into in voltage form, and it will send a signal to the Node MCU. Alright, so let me demo. So you can see here, now it's like 0.02 watt, and then when I turn this lot on, you can see the lot is now moving, and you can see now it's drawing 6.81 watt. And then this cost is the amount that is consumed by this lot since it started. And this graph, you can use it to track the activity. So now let me turn it off. Alright, this is it for this demo. So in conclusion is, this project, we can install it at any device we want, and then we can use this app as a switch to control it. This current transformer can go up to 100 ampere, so it is also possible to install at the main switch. And actually we also have one voltage transformer that will help us measure the voltage, but however, due to the MCO, it's still stuck in China, so it's unable to deliver here. So I only assume the voltage is 230 for now to calculate the power. Alright, so what is the limitation to us due to the MCO? First one is, there is no tools available for us due to the campus closure. For example me, I seriously need a DMM and oscilloscope to measure the voltage, to measure the power that is output by the current transformer, because it is AC and I really don't want to burn my Node MCU. But however, due to the campus closure, I was unable to enter the campus, so I was only hoping that the experiment won't burn the Node MCU board. Next one is the soldering tools. So due to the lacking of soldering tools, I was unable to present my product in a proper way, which means I'm still using breadboard, and I also cannot produce a proper prototype for this project. And the next one is slow item delivery. For example, the items that I bought from China, the voltage sensor, it still haven't come here and still in China, even though there's almost 3 weeks past, it's still there. And then the last one is accidentally destroy the components. So for example, just now I said the AC. So let's say I was very unlucky and burned the Node MCU, meaning I have to buy a new board again. And I don't think the board will come on time. So this is also an issue due to the MCO. Alright, that's all from our presentation. Thank you.